We move on to the next presentation about Planck, the Jean-Loup Puget, University of Paris 11, the astrophysical result of the high-frequency instrument of the Planck satellite.
Well, good morning. It's a pleasure to be here, and thank you for inviting the Planck two instrument teams to present the results, which are not, as Marco said, the final, but which are pretty close to that. My line of presentation will be trying to convince you that we are going now from what was called the concordance model of cosmology towards something which is now, I think, a standard model of cosmology. And I mean by that something which starts being similar to the standard model of particle physics, which means a model which accounts for many observations with very high precision. And so, but at the same time, have very important open question in physics and in the physics beyond these two models. And that's where the interest lies. And any new physics which would basically be introduced would have to encompass as a subset, in fact, the previous models. So I will start from basically the presentation Marco has done as we shared it, and I will stress now a number of points which will be what I call trying to break the lambda CDM model. And as Marco has said, we have not succeeded to break this model, as also the particle physicists are trying to break and find evidence for new physics. Nevertheless, I will finish by discussing the place where we know there is new physics, which is basically the early universe, and what is the physics which gives rise to the initial condition of the Big Bang, to say it in this way. In fact, I started to do cosmology in the 1970s, and for many years, there was no way to reconcile the few, or not that many, observations in something which was coherent. In fact, cosmology as a science was started, of course, with general relativity and the first models built in the early 20th century. And the first model, which was making simplified assumptions, the most simplest assumptions that the universe was isotropic, homogeneous, and stationary, was the simplest assumption, which was shown to be false very quickly after. So falsification was there, and that was the start, really, of the scientific. And ever since, I think theory has been a step before, ahead of the observation. In fact, there have been predictions of, let's say, at least the simplest models, which had to be checked. And first one was not verified, a number of others were. And we are in this situation, as I will show you. So, of course, the very big step was the discovery of the cosmic microwave background, which was predicted on the basis of explaining why there was 25% of helium in stars, with a relatively constant, and which could not be produced by the nuclear reaction in stars. And so that was the first step. But it's only in the 1980s when we started to get a concordance model which had one piece of evidence that the universe was reaccelerating, and there was that you had to put in the constituent of the universe a third component after the ordinary matter, which has basically energy density in form of mass, but very little pressure, non-relativistic motions. Radiation, of course, the CMB, for which the energy density, the pressure is 1/3 of the energy density, and, of course, a cosmological constant that Einstein had introduced initially in general relativity to be able to have a stationary model. And this is possible when you put basically a cosmological constant or dynamical constituent, which would be a constituent which has a pressure which is minus the energy density. And so that was a key ingredient which succeeded to make the cosmologists fit a model with observations. So, that was this introduction. So, the observation of the cosmic microwave background has became a key ingredient in observational cosmology because it can be observed with really very high signal to noise. And that basically is what was a tool for testing the model. Now, in what I would call astrophysical cosmology, you look at the formation of galaxies, you look at clusters, you look at the large-scale structure in which these objects are gathered and their statistical properties, and that's the other type, and of course the Hubble constant, for example, the expansion. These things are more difficult to measure. For example, the mass of clusters depends on the physics of the gas, properties of the galaxies, the evolution, and so on. So that's much more difficult. And the Hubble constant is notoriously difficult to measure because you have to pile up a number of distance scales. And so we are reaching a point where some of these measurements now are not, I would say something, relatively strong statement that not all my colleagues would probably share, that now CMB is so accurate that it tells you more about the underlying astrophysics on some of these things, measurements, evolution of objects, mass of clusters, and so on, than it tells you about cosmology. There are some measurements which are the baryonic oscillation, which are the same physics as what gives the peaks in the power spectrum that Marco was showing. And this is a geometrical measurement, basically. And so these ones are of exactly the same nature what we measure with the CMB. And as you will see, the combination of these together with the CMB is really an extremely important, not only consistency test, but also test to measure things which are degenerate in the CMB. Now, of course, there are questions. As Marco said, the physical nature of the dark matter or the dark energy is not known. And, of course, the physics at the origin of the two parameters which describe the early universe, the normalization and the power spectrum of the initial fluctuation, is not known either. So we do need new physics, as also the particle physicists need new physics. We have evidence in observation of that, and we still don't know what it is. So it's a very similar situation, in fact. In the hypothesis underlying the standard model, the problem of the origin of fluctuation, which gave rise to all structure, is a very crucial one. And as we know that this structure appeared much before the galaxies and the clusters and the filaments formed, it has to be in a very early phase. And so the only model for that, which had been proposed, it was typically at the same time as the Higgs boson was proposed, and it took to check a number of these predictions about the same time, 25 years or something like that. So Slava in the next talk will certainly talk about that. So the origin of the fluctuation, the only one we know of, is having quantum fluctuation to be at the origin of that. So that has a number of implications, of course, about having a phase which could be an inflation phase, where the universe has expanded exponentially to bring this quantum fluctuation to macroscopic scales. But it has a very important prediction, which is that it should be very nearly Gaussian, and as Marco showed, the spectrum should be almost scale invariant with an index which would be 1, but not exactly 1, because when inflation stops, the large scale and the small scale do not stop evolving at the same time, and so there should be a tilt. So these predictions were a key objective of the Planck mission. I'm showing you here the results of the deviation from Gaussianity. And we looked for it, and this number, there is a FNL, which is just a nonlinear part, which would be deviation from Gaussianity, was predicted to be for the unity. And you measure that by going not to the correlation of 2 points, but the higher order. And of course, if it's purely Gaussian field, you would predict the higher order, and so you can take that out and see if there is any residual, which is what is described here. And you can do that by taking 3 points correlation function, and so the geometry, local, equilateral, orthogonal, is just the geometry of the triangle made by the points you are correlating. And so what is quite spectacular is when you combine now all measurement in Planck, including lensing taken out, and so-called ISW, which is the time-dependent term you have in the fluctuation in the anisotropies, then you get to the numbers which are on the right there, which are typically with uncertainties of a few units for the local ones and close to 1. So we are extremely close to Gaussianity, which is a very important test of this model. Of course, the predictions were that there should be the acoustic peaks, which is just a reflection of that all structure at the same size contract and re-expand in the plasma together. So basically, the bigger structure which has the time to contract once will create the first peak, and the one which are re-expanding would do the third one. And basically, in between, you have a maximum velocity, which gives you the intermediate peaks. So that was a prediction very early, and it was predicted to be a very interesting tool to measure cosmology. So I jump over that. And of course, the polarization is also a key ingredient which enables independent measurement of some of the key parameters. So I'll come back to the end. That's what has been shown by Marco, and I would repeat that the temperature determination of the parameters and taking the parameters with the polarization, we have put on the right column the difference between these two in number of standard deviation. And you can see basically that the largest deviation is 0.2 sigma, which means that we have two completely independent measurements, measurement of the polarization, measurement of the temperature, which tell us the same story. We can use one or the other or both of them, and it tells exactly the same story. And when we saw that, that was, I can tell you, that was really something. It shows that this model itself will stay. It will stay as a subset of larger physics, but it will have to contain that because it's what leads to this model is so stable. Now it was known and shown in great detail, especially by George Stasiou and Dick Bond, that there are a number of degeneracies between the parameters, and there are one which is a major one, which is called the geometric degeneracy. If you plot the matter density in the universe and the so-called lambda, which is the dark energy term, which is, as you saw and as you know, 70% of the total energy density. In this diagram, you could build models which fit the same CMB. And the dashed line is the sum of these two, which is equal to 1, which will make a flat space universe. And the color is just the Hubble constant that changes. And so with CMB alone, with temperature CMB alone, you cannot resolve that. Now, which is very important is that in the early days of CMB, especially WMAP, the WMAP was using independent measurement of the Hubble constant to break this degeneracy. And it showed that basically we were close to the Euclidean space. Now with Planck, the lensing gave us a completely independent measurement, a geometrical measurement. It's just the lensing of the CMB itself coming from a redshift of 1,000, going through the structure and being distorted by the structure. And that gives a non-Gaussian term, which you can extract from. And so when you extract that, you can remove this degeneracy, and you can see that basically coming from the contour there, where you could be quite far away from for example, a flat space, the blue contours on top was what you can get with lensing. And now, using astrophysical measurement, which is the Baryon oscillation, the measurement of galaxies, both projected in the sky and also in velocity, which is lensing plus BAO, then you get to the small red spot. And so everything converges towards a Euclidean space with a very high accuracy. I will show you the number after. That's the lensing itself. So you can measure this lensing. So it's lensing by the structure. So it's not now physics being done at the redshift of 1,000. Now it's the imprint of the structure in the universe, which changes somewhat the CMB at redshift of a few. And so it's a measurement of a much closer to us in time. And so you can basically build a power spectrum, and the prediction of the best model is a curve, and the measurements are on it. And you see that basically it's also a 40 sigma detection of this lensing. So once again, not only the initial conditions are what they are and measured as they are, but when you propagate them in the formation of structure and say how much this structure would distort your CMB, it fits, which means the story that we see at a redshift of 1,000, you can propagate it to a redshift of a few, and it still works. Still works within a caveat on which I will come. This is a caveat. The lensing is changing the peaks. The peaks are widened a bit by the lensing. You can understand that when you have a peak which is structure of all the same scale, same size, angular size, when they are lensed, of course you deviate the radiation, and so basically you broaden that. So that's the way the CMB detects the lensing. Now you can also measure the spectrum I just showed you before. So when you look at the broadening of the peaks, you find that you would like to have a slightly higher lensing by typically 2 sigma, 2 standard deviation. And when you look at the level of the lensing spectrum, you find that you measure a slightly lower one by a fraction of a sigma. It's not big. It's uncomfortable. It might tell us something we don't understand. So that's one place. We had something a bit similar with more astrophysics measurement. I will not discuss that. I think, as I said, that it tells us more about the astrophysics than about the cosmology. So I will not discuss, for example, the clusters. I will go to polarization now and measurement of tau and trying to look for the B modes, which would be a sign of the gravitational waves produced in inflation, if there were. In the Planck HFI, we measure polarization by combining measurements of bolometers, which are polarization-sensitive bolometers. You basically absorb the radiation in a set of wires, and so you are sensitive to polarization. And you combine at least 3 of them to get the polarization. So you understand very easily that if you want to measure a polarization which is 1% of the fluctuation of the CMB, you need to have an intercalibration of your bolometers, which is extremely accurate. And to take advantage of the signal-to-noise we have in the high-frequency instrument, we knew that we needed intercalibration at the 10⁻⁴ level. What is shown here on the top panel, it goes from Q, V, and W are the 3 channels from WMAP at 24, 60 gigahertz and 94 gigahertz, and then all the channels from the low-frequency instrument and high-frequency instrument of Planck. And it's a relative calibration. And you can see that basically everything, if you look at the central part, starting at 44, going to 217, it's basically within 0.1% of intercalibration. And I can tell you that now, within the detectors at 100 gigahertz, the dispersion of the calibration between the 12 detectors is 5⁻⁶ RMS. That took 3 years to get to after we got the data, but we are there. And so now we have really a very good tool to measure polarization, including on very large scales, which is very interesting. Now, it's just something which is more interesting for astrophysicists, is that with 44 gigahertz, the low-frequency instrument is intercalibrating with the VLA, which is a big interferometer in the US, in New Mexico. And so calibration now of radio astronomy done in this gigahertz frequency range will be intercalibrated with a cosmic background. Now we go to 545 gigahertz and intercalibrate also. That's a calibration on the CMB itself. And that will give, for example, for the Herschel observatory, which observed all the way to the far infrared, also brought back the calibration within 1% of the measurement of the CMB. So astrophysics will now benefit through Planck calibration, which are better than the percent level from radio astronomy in the gigahertz regime to the far infrared. And I've been doing photometry in the far infrared 20 years ago, and I can tell you that when we were at 10 or 20%, we were happy. So that's a very, very significant technical issue. One of the parameters is the ionization. How many electrons, what is the optical depth of electrons from the time the first objects forming reionized the universe. And you could see a set of determination of the likelihood of tau. And you can see that, for example, Planck temperature only gives you the blue curve, which is quite high. And we know it's not an accurate determination of that. You can see a number of other combinations. I'm not going to detail all of them. And that has used the low-frequency instrument, large scale. It has not used the high-frequency instrument data on polarization, EE, at large scale, because we knew that we had systematics which would prevent us to do that and to do a measurement on also the B mode. In fact, the data which is being released within a few days, which are the 2015 data, will be tagged saying, please don't use that to try to do cosmology with the HFI data at very large scale. We have succeeded to find what are these It was mostly the intercalibration and just another systematic we're not seeing. So the 2016 will be clean at the same accuracy for large scale than we had been for the small scale structure, which is very good. I would not have been saying that if I had been speaking a month earlier. So, just to illustrate the comparison with the geometric astrophysical measurement of the baryon acoustic oscillation, which is basically looking at regroupment of galaxies coming from basically what would be the first peak at a redshift of 1,000. And you see that the best measurement now of BOSS, the red error bar, which is called BOSS CMAS, is basically completely consistent with the gray band, which is a prediction as a function of redshift of this baryon acoustic oscillation from Planck. H0, it was already mentioned. In fact, there was a revision of some of the Hubble constant, which in the distance scale, for example, has a mega maser in one galaxy, which is a key single point measurement, and which basically, so Hubble constant is, sorry. Just a few things. So the physics which goes into describing what we see is at the level of the recombination, when basically the universe has cooled down to 3,000 Kelvin and the hydrogen recombines. And so basically it decouples almost completely the radiation from the matter. So the physics of the recombination is key, and it was known, and a number of people developed a much more accurate physics of that. Something which is almost you could say, oh, if I had not measured the temperature of the CMB, or if I don't know what is one of the key elements, which is the 2-photon decay of the forbidden transition between 2s and 1s in hydrogen, what cosmology is telling us? Well, cosmology is telling you that basically the temperature is a bit above 2.72, which is pretty good. And you could see the distribution of likelihood that the cosmology will tell you about this atomic physics transition, where you could see that the theory, quantum electrodynamics tells you. Same for nucleosynthesis. I will not describe that in detail. Just looking, you have here the baryon density in abscissa on the right plot, and the red band is the Planck measurement. And you can see basically, if you look at the bottom, the deuterium predicted is a green curve, which cuts the red curve, where the best measurement, Cook et al. 2014, is. So basically, yes, the prediction that there should be a CMB because hydrogen, deuterium, and then helium had been produced in the Big Bang was right. Okay, let me go quickly to neutrinos. You can measure the number of neutrinos from the CMB because they are free streaming outside of structure, and so the formation of structure is clearly dependent on the number of relativistic species. The effective number of neutrinos is there, and it's 2.94 plus or minus 0.38, 95% confidence limit. So basically, Planck is ruling out an extra number of neutrinos. The sum of the mass of neutrinos, same limit, is typically 0.2 eV, and it's improving. So we see that now cosmology is giving also strong constraint within the model we are developing, of course, on neutrino numbers, neutrino mass. And it's going to go on. On the decay of dark matter, we also have now also relatively strong constraint which exclude, in fact, the interpretation of some of the gamma ray results as being decay of dark matter. Let me come now to the last thing. Inflation is producing quantum fluctuation of the energy density. It also induces in gravity waves, and the various models of inflation can predict very different levels of gravity waves. These gravity waves are imprinting a specific mode of polarization on the CMB, both at recombination and at reionization when, again, we have free electrons. And so we can look for these modes which are the ones which are not parity invariant, kind of helicoidal type. That's a very, an objective which is very hot topic for observation in CMB, and you could see the two types of polarization schematically shown here. The first line on top is the temperature. The middle one is the EE, the one which is parity invariant, and the bottom line is B modes. And you can see basically, depending on the amount of tensor mode you have at the very beginning, emerging from inflation, how much that does, and that's a red curve, and you could see for 10% or 1% tensor mode, that you will have this red curve, and that's very low level. It's 10 minus 2 micro K square. Remind you that the first peak in T is 6,000 almost. So we are now a factor of typically 10 to the 5 below the first peak. Where are we on that? People working on inflation like to do a plot of the so-called primordial tilt. This tilt compared to scale invariance, which is on the bottom, and the prediction, I'm sure Slava will explain to you why it should not be 1, but it should be something which is typically predicted for the simplest model around 0.96 to 0.97, and that's the level of the B modes on the top, with typically 10% near the top of these curves. And I'm not going to describe that in detail, but we have ruled out many of the more complicated, multi-field and so on things because of the Gaussianity and because of these values of R. We need to take the dust out because the dust is polarized, and it gives, we were expecting it gives as much B modes and E modes, which is not exactly true. You will have the E modes and the B modes. That's the power spectra of the dust. You could see the cosmology that we are trying to detect, E modes and B modes. And you see that there is basically power law of the dust emission. You could see basically on the right plot, as a function of frequency, the dust on the high frequency side. And so the BICEP team, which is a ground-based experiment at South Pole, which has a much larger number of detectors. We have 12 bodometers per frequency, and they have 500, and with the Keck data, there are more than 3,000 detectors. So they improved the sensitivity, and they looked at a small piece of sky visible from South Pole, which was one of the cleanest regions in terms of intensity. That's the polarization representation of the dust from the 353 gigahertz channel. And what you can see on the right side is tracing the magnetic field from our own galaxy with the dust polarization going through the white contour, which is the BICEP field. So you see that basically we can measure the galactic magnetic field with the dust emission in this field. So first look, you have to take it out before you can say something about it. And the very clean regions are in blue for the galactic South Pole and the north. And there are regions which are clean, and they are not exactly correlated with intensity. So that was a prediction of what the B modes should be in this field for the average density, and the BICEP team asked us to collaborate and basically do the correlation between the 353 and their data. So that's the lensing mode as a function of the multipoles. You can see on the right polar bear and other experiments, and you could see on the left side the boxes, the blue boxes, which are the BICEP measurement. And you could see the excess at L equal typically 50 to 100, which was taken to be the B mode, the primordial B modes. There are B modes. The line, the black line, is a prediction of lensing converting E modes into B modes. That's a strong prediction. Last slide is coming. So what we did after the prediction is on the top left, you could see the prediction of the lensing B modes for the best Planck model. You could see that the black dots, the measurement of the BICEP team, and the blue is after removing the dust, which is a very good measurement of the B modes lensing induced, which is good, but which is not the primordial B mode. You could see the upper limits, so you can see that it's still compatible with 0, and we'll need better measurement to do that. So that's one of the obvious goal of CMB experiments, which would combine probably for a while Planck data together with ground-based data on transport. And I think I will finish that on showing also and reminding you that Planck has been the collaboration for many groups and many universities and many agencies, and we should not forget about that. Thank you.
Thank you, Jean-Loup, for this very comprehensive presentation. Time for one question, because we are a little bit late. If there is any very urgent question. Yes, one there.
Yeah, you've shown us very beautifully the accuracy of the data that Planck is giving to us, both you and the previous speaker. The consistency also between the temperature results and the polarization results. All this is very nice. But the question is, why should we call this a model? Even a standard consensus cosmological model. To me, this is just a maybe precise representation of our ignorance. We don't know anything about dark energy and dark matter. This is not just semantic. A model, for me, is something that comes from an idea, possibly a clever idea, about some new physics. And then we go and check the model with the observations. What happens here is the opposite. Observations are telling us that there is some new physics which we don't know about. So why should we call this a model? Thank you.
You're right up to a point. It's not a model, but the inflation, let's call it a paradigm, which means if there is a field which would create in general relativity, if you put a term, either cosmological constant, and that fit in general relativity, Einstein said it, of course you have no problem to this, or a field, a scalar field, which would basically create an exponential accelerated expansion, you do predict that you could explain the fluctuation as a quantum fluctuation, and it has prediction. It has a prediction on the Gaussianity, it has prediction on the tilt, and that was predicted in 1981. And next talk will go on that. And that was checked only very recently. So what, if it's not exactly a model, is still something which would have a phase of this type for which 3 predictions have been verified. There is no prediction about the level of B modes. If we find them, that would help and give a tool to study this, the physics of that. That's why it's so important. There is not a definite prediction of lower limit and so on. So the rest of it is the physics of the standard model, which is in there, and you cannot touch much, not only because of the accelerator measurements, but because of that. And for example, the three families of neutrinos are comforted by that, and cosmology, first order, forbid to have a fourth type of neutrinos. So the standard model, as it's called, of particle physics, did not tell you that, for example. And no model of cosmology tells you that, but the observation and the link between the two tell you that. So I don't know how you want to call that, but it's...
Okay. Thank you so much again. This was a very interesting question and presentation.